Constant volume calorimetry. The drawing shown here is a bomb calorimeter. This is a device that is actually used to determine how much energy food contains. This is an enclosed steel case. Outside the case, it's surrounded with water. The heat that's released as the food or whatever substance you put in here is burned is absorbed by the water, which then causes the water to go through a temperature change. You can measure how much heat is released from the substances burned inside this enclosed steel case by measuring the temperature change of the water and using MC delta T to find the heat released. These are called constant volume calorimeters because this is not allowed to expand. Everything takes place inside this little steel chamber. As I said, the water is outside, and so the water outside absorbs the heat, and then that heat is measured through a temperature change. A 0.5268 gram sample of octane, formula C8H18, is placed in a bomb calorimeter known to have a heat capacity of 11.3 kilojoules per grams or per Celsius degree. The specific heat capacities of bomb calorimeters, notice the units are different. It's kilojoules per Celsius degree. There are no grams involved here. This is just the heat capacity of the calorimeter itself. That is the calorimeter parts and the water parts all combined together because they all absorb the heat from the calorimeter. Go back and look at this. The heat released has to go through the metal to the water. So the combination of the water and the metal together is where that specific heat capacity comes from. So the octane is burned in a bomb calorimeter known to have a heat capacity of 11.3 kilojoules per Celsius degree. The octane ignited in the presence of excess oxygen, and the temperature increase of the calorimeter is 2.25 degrees Celsius. How much energy is released? For these types of problems, to find the energy released by the reaction, you just multiply the temperature increase by the specific heat of the calorimeter, and that will give you the energy released. So we have our temperature change. Temperature increase goes here. We have our specific heat of our calorimeter. So we're just going to multiply 2.25 degrees Celsius by 11.3 kilojoules per degree Celsius. And that's what I've done. And I've gotten, that gave me 25.4 kilojoules. What this tells me is that when 0.5269 grams of octane burned, 25.4 kilojoules of energy was released. I need to know per mole. So I will change the grams of octane to moles by dividing by the molar mass of octane, and that gives me that I burned 4.614 times 10 to the negative third moles of octane. If I want to know the kilojoules per mole, I will then divide my kilojoules by the number of moles that I burned, and that will give me the 5.5 times 10 to the third kilojoules per mole. But since this was an exothermic reaction, I have to remember energy was released, therefore the sign is negative. So remember, when doing bomb calorimeter problems, the formula is simply the temperature change multiplied by the specific heat of the bomb calorimeter, which will have to be given to you. Once you find the energy released, that will be per however much, whatever sample size they gave to you in the problem. You need to convert that to moles and then divide your kilojoules by your moles to get kilojoules per mole.